Hello friends, and this video is going to be on electrical potential and electric field. Here we're going to talk about different power sources like batteries, power lines that carry electric power to our homes and to the factories. We'll even talk about the electric clouds that give out a lot of electrical power in the form of lightning. And also the communication system built up in our bodies, where all of it is done by tiny electrical currents. Electric potential is similar to gravitational potential. And we know that when you have a mass at a certain height, it has gravitational potential energy. And that is given by the formula mgh. So at a certain point, the gravitational potential is actually g times h. And when you keep that mass at that point, the potential energy becomes mass times the gravitational potential. So you see the connection there is that potential energy, gravitational potential energy, is mass times the gravitational potential at that point. In a similar way, the electric potential energy of a charge at any point is actually the charge multiplied by the electric potential. The charge multiplied by the electric potential. From this formula, where it says electric voltage or potential is potential energy by charge, which means when you take the charge to the other side, you're going to get potential energy is equal to charge multiplied by electric potential. So electric potential is a function of a point in an electric field, and if you keep a charge at that position or at that point, that charge is going to have electrical potential energy. Now this diagram clearly shows an electric field where you have two plates set up, one plate positive, the other plate negative, and the electric field is from the positive to the negative. And so if you have a free positive charge, that charge would love to be on the negative plate. See, that would be, it would try to be on the negative plate. Now if you had to move the charge from the negative to the positive plate, we have to do work. This is similar to lifting an object in the gravitational field. You want to lift an object in the gravitational field against gravity, you got to do work. And in doing that work, we give it potential energy. In a similar manner, when you move that positive charge from the negative plate to the positive plate against the forces of repulsion, we are doing work on the positive charge, thereby giving it potential energy, electrical potential energy. So that's the relation. We do also know that if the positive charge is free, then it will by itself move from the positive plate to the negative plate. And in doing so, it loses potential energy. and that means the potential energy gets converted into kinetic energy. Excuse me. It's just like when an object is dropped from a height. At that height it has gravitational potential energy, but when it falls to the ground, the potential energy changes into kinetic energy. So the same is the case here. And so the work done is equal to the negative of the change in potential energy. Work done is the negative of the change in potential energy. And so we can define electrical potential or electric voltage as the ratio of potential energy to the charge. This gives us the formula: voltage is equal to work by charge. And in putting the units, we see that the unit of work is joule, the unit of charge is a coulomb, and therefore the unit of voltage becomes joule per coulomb, which is also called a volt. This brings us to the idea of potential difference or voltage. So let's get into the idea of potential difference or voltage. Now we have a car battery here, and we see that one of the terminals is negative, the other is positive. The negative terminal is assumed to have a potential or a voltage of 0, while the positive terminal usually has 12 volt. So we say that the potential difference between the negative and the positive is 12 volt. In electrical terms, the negative terminal is always considered to be ground, and ground is considered to be at 0 volt. So the voltage difference or the potential difference between the negative and the positive is 12 volt. Now we will interchangeably use the words voltage or potential difference to be the same. And the term voltage shows how much work has to be done in moving a charge from one terminal to the other. As we can see here, voltage is the same as potential difference, and we arbitrarily assume that the voltage is 0 at ground or the negative of the battery. With electrons and protons, we're going to be talking about very small charges, and therefore it's convenient to define another unit of energy called electron volt. The electron volt is the energy required to accelerate an electron through a potential difference of 1 volt. So the energy required to move an electron, to accelerate an electron through a voltage of 1 volt is called 1 electron volt. And 1 electron volt is 1.6 times 10 to the negative 19 joules, because it's just the charge of the electron multiplied by 1 volt, which means 2 electron volts would be the charge of the electron multiplied by 2 volts. You got it. So you have to do greater work in order to accelerate an electron through a greater voltage. So that's a new unit of energy. And just to understand, now in order to break down organic molecules, to break them into their constituents, about 5 electron volts. But in the case of a nuclear decay, we see that the energy involved in the emission of alpha, beta, gamma rays, for example, the energy involved is much higher, and it is 1 mega electron volts. That's 1 million electron volts. So now we have to consider the electric potential in a uniform electric field. So we can set up a uniform electric field by having 2 parallel plates with one positive, the other negatively charged, as shown in the diagram. And that sets up a uniform electric field. That means the strength of the electric field is the same at every point. Now, in this particular case, if the strength of the electric field is E, Newton per coulomb, and if the distance between the plates is d, then the voltage between the plates VAB is simply the product of the electric field and the distance between the plates, which when we rearrange, we get the electric field to be the voltage divided by the distance between the plates. And that gives us a new unit for electric strength or electric field, which is volt per meter. Volt per meter. Now here is a simple example. So if we have a voltage of 12 volt between two plates separated by 1 centimeter, changing the centimeter into meter, we have 1/100th of a centimeter, which is 0.01 meter. And so we get 1200 volt per meter as the electric field strength between the plates. So that's the relation between electric potential and electric field. And now we have a particular case of electric potential due to a point charge, which means if you have a charge at a certain point and you want to find, so let's say you have a charge at this point and you want to find the electric potential somewhere in the electric field, so let's say at this point, and let the distance between the charge and that point be r, let the magnitude of the charge be q, then the electric potential at this point is simply kq by r. So electric potential due to a point charge is kq by r. Remember that k has a value 9 times 10 to the 9. So if we simply calculate, as an example, if you have 1 coulomb and then you want to find the electric potential at a point P, which is 1 meter away, we're going to get a huge voltage, 9 times 10 to the 9 by 1 by 1. Because the charge is 1 coulomb and the distance is 1 meter, which gives 9 times 10 to the 9 volt, which is really big. This shows that a charge of 1 coulomb is actually a big charge because it sets up such a huge voltage. And that's why usually we talk about micro coulombs and nano coulombs and pico coulombs, etc. Now on the right side that what we have is called a Van de Graaff generator. This Van de Graaff generator has a hollow metal sphere here on top. And there is an electric motor down below with a pulley. This pulley is very important because it's able to get charged. This pulley gets charged, and then when it gets charged basically by friction as the motor works, and when it comes to the sphere, the pulley transfers its charge to the sphere, and this process continues. The pulley gets charged and transfers to the charge to the sphere, and within a few minutes the sphere becomes highly charged, and therefore the voltage around it becomes so high that the air becomes conducting and the sphere discharges. This is just like lightning produced by clouds. When the charge on the clouds builds up to such a high value due to friction, and then the voltage increases to such an extent that the air becomes conducting and the cloud loses all of its charge to the ground or to a tall building somewhere when it could be really dangerous. So it's basically discharged. So a Van de Graaff generator is used to show the same phenomena in the physics lab. We have the concept of equipotential lines. These are lines where the potential is the same throughout. Now, as an example, if you have a point charge Q at all distances that are equal from it, we will have the potential to be the same because voltage is kQ by R. So if R is a constant, then the voltage is going to be same. That means in the sphere, although you see it as a circle, it's 3D and it's a sphere, you're going to have at all of these points, the voltage is going to be the same. Same thing here, the voltage at all of these points is going to be the same, but the voltage on these two spheres are not equal, because as you go outward, the voltage decreases as R increases. But all of these spheres are equipotential surfaces. And imagine that you want to move a charge from this point to this point on the same equipotential surface. How much work do you have to do? Well, by definition of potential, you don't have to do any work, because the potential at these 2 points are the same. The work done is zero. So remember that the work required to move a charge between any 2 points on an equipotential surface is zero. Another very important point is that equipotential surfaces are always perpendicular to the field lines. Equipotential surfaces are always at right angles to the field lines. So if you know that the electric field at a certain point is this way, for sure the equipotential surface at that point would be at right angles. So when you look at this diagram, you see that the electric lines are shown moving from the positive to the negative. Look at the arrows. And so those are the electric lines, the ones with the arrows. But the circular shaped ones are the equipotential surfaces. And at every point we can see that the electric line is perpendicular to the electric field at that point. At every point that is true. See, look at that. So at this point you can see it's 90 degrees between the electric line and the equipotential surface. So that's a very important point to remember. Let's talk about an electrical conductor that is charged. The surface of a conductor is always an equipotential surface. So a surface of a conductor is always an equipotential. So if you have a spherical conductor, hollow for example, that is charged, and you look at the potential at every point on the surface, it's going to be exactly the same. It's going to be an equipotential surface. As shown in this diagram, between 2 plates are evenly spaced and parallel. So this is the negative plate, and as already explained, the potential at a negative plate is taken to be 0 volt, and as you move to the positive plate, you can see that the voltage increases, and at the positive plate it becomes 100 volt. And if we draw equipotential surfaces at 25, at 50, 75, and of course at 100, you see that the voltages or the spacing between the lines is equal. And also note that these equipotential surfaces are at right angles to the electric field, as explained on the previous slide. Parallel plate capacitor, where we have 2 parallel plates, metal plates, separated by a distance, and that's a parallel plate capacitor. And usually we could have an insulator between them, which could also be air, as in this case. And in order to charge a capacitor, the plates are connected to a battery, and the plate connected to the positive terminal of the battery gets positively charged, and the one connected to the negative terminal gets negatively charged. And the maximum voltage between the capacitor plates will always be equal to the voltage of the battery. That means if it's a 12 volt battery, after the capacitor is fully charged, the voltage between its plates will be 12 volt. That's what it means. And when the capacitor plates are disconnected from the battery, the capacitor is able to hold that charge. And that's why we say that a capacitor is a device used to hold electrical or store electrical charges. It can be stored by a capacitor depends on the voltage that's applied between its plates. That means the voltage of the battery. And it also depends on the physical characteristics of the capacitor, which means it depends on the area of the plates of the capacitor, the distance between the plates, and also depends on the nature of the insulator between the plates. Before we get into calculations, the fundamental formula for capacitance is it's the ratio of the charge to the voltage. So C is equal to Q by V, which enables us to define the unit of capacitance, which is called a farad, and 1 farad is 1 coulomb over 1 volt. 1 farad is 1 coulomb divided by 1 volt, and that's a very important formula. Capacitance is the ratio of the charge to the voltage. In this picture, we have many kinds of capacitors, as you can see. These are the different kinds of capacitors. You have ceramic capacitors, electrolytic capacitors, and so on. And the fundamental formula for capacitance of a parallel plate capacitor is given by epsilon naught A by D. C of a parallel plate capacitor is epsilon naught A by D. This is for a capacitor which has air between the plates. Here epsilon naught is the permittivity of free space, which has a value of 8.85 times 10 to the negative 12. A is the area of the plates, of course, in meter square, and D is the distance between the plates. So here is a quick example. So epsilon naught is 8.85 times 10 to the negative 12, and I've assumed that the area of the plates is 0.01 meter squared, and that the distance between the plates is 10 to the negative 4 meter. Now that's small, you can see, especially because it's in meter. That's 0.1 millimeter. So usually the plates are really close to each other. So when you do the calculations, you get the capacitance as 8.85 times 10 to the negative 10 farad, which is 0.885 times 10 to the negative 9. And why did we have to write it in terms of 10 to the negative 9? Because then it can be expressed as nanofarad. Nanofarad, 1 nanofarad is 10 to the negative 9 farad. So we get 0.885 nanofarad. So this is how the capacitance of a parallel plate capacitor is calculated. Now, so far we were talking about a capacitor with air as the dielectric, or air as the insulator between the plates. But if we have another material between the plates of the capacitor, what's going to happen is, because of the electric field, the molecules of the dielectric or the molecules of the insulator will be polarized. What does it mean by polarization? It means that the center of the negative charges and the center of the positive charges usually are right at the same point. But because of this electric field, we can see that their centers are slightly shifted. See that the center of the negative charges moves to the right side and the center of the positive charge moves to the left side because of the nature of the electric field. So because their centers, instead of being at one place, are now separated, we call it polarization. So that's actually a polarized atom. So because of this polarization, what happens is there is a reverse electric field set up in the material. So remember that the plates were positive and negative on the left and the right. So the electric field was originally from positive to negative in the capacitor, but because of polarization within the molecules, we have a field that points exactly in the opposite direction. Thereby, the net field decreases. When the net field decreases, that means the voltage decreases, and so the capacitance increases. Remember that capacitance is inversely proportional to the voltage. So as the voltage decreases, the capacitance now increases. Two ways in which capacitors can be combined. One, capacitances can be connected in series as shown in the diagram. You see three capacitors connected to a battery, but they are connected in series to each other. And when the capacitances are connected in series, the total capacitance is given by this formula. 1 over Cs is 1 over C1 plus 1 over C2 plus 1 over C3. So that's how the equivalent capacitance is calculated. Now, what do you mean by an equivalent capacitance? It is that capacitance which can effectively replace all those connected in series, which means this single capacitance has a value Cs in parallel. And that is what is shown in this diagram. In a parallel connection, each capacitor is individually connected to the battery. So that means in a parallel connection, the voltage across each capacitor is the same as the voltage of the battery, which is not true in a series connection. So that's how you know that it's a parallel connection. Again, in a parallel combination, the voltage across each capacitor is the same as that of the battery, because each one is individually connected to the battery. And to find the total capacitance of a capacitor, we just add the capacitances. That means to replace all these three connected in parallel, we just had to have a capacitance which had the sum of all the three. So that's the formula for total capacitance of capacitors in parallel. Here is an example of three capacitors that are connected, with two of them connected here, C1 and C2, and a third one connected here. So when we look at this diagram, we can understand that C1 and C2 are connected in series, while that combination is connected in parallel to the third one. Therefore, if the values of these two are given, we can use the formula 1 over Cs is 1 over C1 plus 1 over C2 to find that the capacitance of these two effectively is 0.833 microfarad, which is represented here now. Once you get this to be 0.833, these two are now connected in parallel. So to find the total capacitance, we just need to add their capacitances. So the total capacitance is 8 plus 0.833 microfarad, which gives 8.833 microfarad as the capacitance. So this is how problems are worked out dealing with combination of capacitors. Capacitor stores charge. Effectively, it stores energy. And you can see that the flash in a camera is actually a capacitor discharging. It stores the charge and then discharges, giving out light. And here, the formula for energy stored in a capacitor is 1/2 CV squared. So there are three ways. We'll get to that. But before that, remember that capacitors store energy that can be utilized in defibrillators, and as already explained, camera flashes. But the formula for energy stored by a capacitor can either be 1/2 times CV squared, or Q squared by 2C, or QV by 2. So these are the three formulas used to find or calculate the energy stored by capacitors. Now, thank you for watching this. Remember that I'm working out 10 problems from this chapter, so make sure that you study those 10 problems in order to make the learning of this chapter complete. Thank you. See you soon.